Okay, we'll jump back in. We've covered a lot so far, right? I've given you guys the units of measure, the forces that govern interactions between matter and energy. We learned that matter and energy were just sort of two sides of a similar coin, right? We learned about the unit systems, the metric system, the prefixes, abbreviations. I taught you about orders of magnitude. So think about all the stuff you've learned already in just hour or so. Now we're going to try to move on and complicate things a little bit. So now I want to talk about the physics of energy. So let me briefly describe what we mean by physics. So the whole field of physics, big complicated field, it means a lot of things to a lot of people, but I think roughly speaking, as a good sort of general idea, physics is the study of how things move. Okay? That's what it is. It's the study of the world and what's in it and how those things interact with the other things. Okay? Study of how things move and interact with each other. Okay, so now we're going to talk about the physics of energy. So how does energy interact with matter? How do those things affect each other? So there we go. So let's the first thing we want to do is we want to give a definition of the word energy. Okay, so maybe some of you read, maybe you haven't, maybe you have your own idea. What is energy? So kinetic is a type of energy, right? It's the energy of movement, right? But there's also potential energy, the energy of your position, right? There's also mass energy. I'm just sitting here not moving, right? I still have energy in the form of my mass. Remember, mass equals energy, E equals mc squared. So I've got energy. If I move, I have more of it, right? But I have some just being here on Earth and being massive. So what's energy? Yeah, that's it, right? So to restate that again, Lewis correctly tells us energy is the ability to do work. So then this is why I don't like that definition, because then you have to go, well, what do you mean work, right? So then you have to define work, right? Work is the change in motion or state of an object. So to change the position or velocity of an object. That's it. That's what work is, okay? To move things. That's why I said physics is the study of how things move, okay? Energy is the ability to do work. Work is moving things, right? Think about like, having a pulley, right? And a weight on the other end of the pulley, right? That weight's on the ground, and I want that weight to go up higher. What do I have to do? I have to pull down on the pulley, right? Pull down on the rope that's attached to the pulley. And what is required to lift that weight? I don't know that everyone's picturing what I'm picturing. So, all right. So imagine you have a pulley system here, okay, and you have a rope goes around the pulley and is attached to a weight. Let's say the weight weighs 1 pound.
Let's work on your triceps.
Let's say the weight weighs 1 pound, okay?
Yeah.
And it's on the ground. So it's on the ground, sitting stationary, okay? If I pull down on that rope, the weight goes up, right? What have I done to the weight? Think about its position and velocity right now. It has a position. There it is. Is it moving? No. Okay. When I pull on that rope and pull downward, I'm going to pull that weight upward, right? What's changing about that weight?
Distance.
Not distance. It's moving a distance, right? So you're getting at something. When I pull down on this rope and this weight goes up, how does its position change? Or does its position change? Yes. Okay. The weight goes up, right? Okay. So I've changed its position. And as I'm pulling it, the weight's moving, right? Distance over time is velocity. So as I pull on that weight, I'm changing its position and velocity. Okay? Said in another way, I'm doing work to the weight. Okay? In order to do work to something, what did I have to use? Energy, right? It took energy for me to pull down on that weight, right? I've got to use like a pound of force to pull down on that weight, yeah, to pull it upward, because it's not like a compound pulley system. It's just a simple pulley. I've got to pull with that amount of force, okay? Energy is the ability to change the motion or state of an object, okay? You know, take this little pen cap, right? There it is, sitting on the table, not minding its own business, right? It has a position and a velocity, right? How much distance is that covering over any given amount of time? Like 0, right? It's not moving, right? Assume the room is, assume we're stationary, right? Relative to the Earth's surface, we're not moving right now, right? So that pen cap is stationary, and if I leave the room, assuming none of you mess with it, and I come back in a year, and assuming no one coming in and messing with that pen cap, where do I expect the pen cap to be when I come back to it? Right there, right? Why do I expect it to be right there? No outside forces have acted on it, right? No forces have acted on that, so we expect it to be in that same spot because no one has put any energy into it, okay? No one has done any work to that pen cap, okay? However, my cat comes along and bats the pen cap, right? What did we do to the pen cap? I put energy into it, and I changed what about it? Its velocity and position, right? I changed position and velocity, yeah? Which is motion and state, okay? I've changed its position and velocity. Now it's over there on the floor, and while it was flying through the air, it had a velocity, right? It was greater than what it had sitting on the table. Okay, so there's a unit of energy that can be applied to the amount of energy it took to move that pen cap, as well as the amount of energy it takes to raise that 1 pound weight. We have a unit of energy. That unit of energy is called the joule, okay? Joule, joule. The joule in everyday, in using an everyday concept, is enough energy. Energy is given as a capital E. You remember that from E equals mc squared. The joule is enough energy to move a half of a kilogram object to a rate of about 16 kilometers per hour. So put 1 joule of energy into a roughly 1 pound object. Put 1 joule of energy into it. Let's say you hit it, right? 1 joule of energy into a roughly 1 pound object. It's going to now start moving at 16 kilometers per hour, okay? And it will continue to do that until some outside force acts on it, right? If we're here in the room on Earth, what kind of outside forces might act? Let me go back to the pen cap example, okay? So the laws of motion and the laws of physics say if I put energy into that pen cap, it's going to start moving, right? And it'll keep doing that. So if I flick it, it's going to have some initial velocity, right? If there's no outside forces acting on it, that pen cap will just sail off for forever, okay? What outside forces are there here on Earth in this room? Gravity, okay? And what does gravity do? It's attractive, right? Don't say pulls down, because gravity on Earth pulls down, but gravity's attractive, right? So here on Earth it pulls down. We have a direction of gravity on Earth, okay? So gravity's gonna pull on the pen cap. And what else? What other outside forces do I have? Yeah, that's why I said on Earth and then in this room, right? We have air in this room, right? So how does air affect the motion of this thing? Friction, right? We're interacting with the air in the room. The air is kind of like a liquid. It's a gas, but it acts kind of like a liquid, right? You can wave your hands around and feel the air in the room, right? There's some resistance on your hand as you're waving your hand around, okay? So again, I flick that pen cap, right? And it follows a trajectory. That's pretty good, right? It went up. I don't know if you watched it, but it went up, and then it went down, right? Okay? It follows a path that gravity's pulling it along, right? Follows a trajectory. It has an initial velocity, and it is slowed by the air in the room and the forces of gravity, okay? I did work to the pen cap by flicking it, okay? I put energy, I used energy to do work to the pen cap, changing its position and velocity. But then some outside force came and acted on it, okay? So now imagine that we are, for some reason, up on the outside of the International Space Station, right? We got spacesuits on, same pen cap, we set it down on the outside of the ISS, and then I flick it, okay? What's that pen cap gonna do? Straight, right? Because there's, for our purposes, let's say no force of gravity, okay? There's no force of gravity acting on the pen cap, and there's no air, okay? So that pen cap is going to have an initial velocity, however much energy I put into it, it's going to be traveling that fast, right? And it's going to go in that direction. Notice the pen cap went in that direction, towards the back of the room, not that way, right? So there's a direction that the force is applied in, okay? And if I do that on outside of the International Space Station, flick the pen cap, it continues with that same velocity and along that same path indefinitely, okay? Is it ever going to change its velocity in that path? No, unless what? Some outside force acts on it, right? So someone else comes and smacks it as it flies through the air, right? It runs into a meteor or gets pulled into like the moon's gravity or back into Earth's gravity, right? Or gets pulled towards the sun or any number of things, right? The point is, though, there's a law of a conservation of energy, okay? The energy that I put into that thing is conserved, doesn't go away, okay? It can convert into other forms, such as when we're here in the room, as that pen cap is flicked and flies through the air, it starts to interact with the air molecules, moving the air molecules around and losing energy because of that. Earth's gravity is pulling on it. It's losing some velocity and position because of that. So there's all of these interactions that we have here on Earth that just don't exist everywhere else in the universe, okay? And so things act just a little bit differently here on Earth, okay? You know, and then this was the insight of Isaac Newton, was that things will continue to move in a straight path with whatever energy they have until they're acted on by an outside force. It's just that here on Earth, things are a little different because we have air resistance, for example, okay, and gravity. So that's the deal. But we have a unit called the joule. We'll use that to talk about energy, because it can be used to talk about things moving, can also be used to talk about like the intrinsic energy in some massive object. So there we are. Energy is a conserved quantity. The total energy within any closed system, such as the universe or a light bulb. A closed system is just any system, anything that doesn't have interaction from the outside, okay? So, you know, we can consider a light bulb a closed system, okay? So for all intents and purposes, nothing's putting energy into that light bulb except for the energy that we put into it, right? The universe is also like that, right? That the universe, there's nothing acting on the universe from the outside, okay? It's a closed system. And so what we say about closed systems, let me give you an example of an open system. I think a closed system will make more sense when you understand what an open system is. The Earth is an open system, okay? Where do we get our energy from? The sun, right? So the Earth's energy is not coming from within the Earth, right? The Earth is an open system because we get our energy from the sun. You're an open system. You don't get your energy from inside your own body, right? You get it from the Earth, right? You eat some plants and animals, right? Those plants and animals got their energy from the sun. You are an open system. The universe is a closed system. Light bulbs can be considered a closed systems. So what we say about closed systems are, any closed system, the energy within that is conserved. It's neither produced or destroyed, it just changes forms, okay? That's important for the universe, right? The universe has a total amount of energy, and it's conserved. It just continually changes forms, okay? So from one form into the other. Mass into energy, energy into other types of energy, right? This is a law called the conservation of energy. It just simply states that energy is conserved within any closed system. So when we talk about like the system of one photon, one atom, that can be a system, okay? One photon interacting with one atom, okay? The energy put into that system has to equal the energy coming out, right? So when we talk about like a photon hitting an atom and scattering, right? If we know what the incoming energy of the photon is, and we know what the scattered photon's energy is, we can know how much energy was deposited into that atom because of the law of conservation of energy. Energy is just not lost somewhere, right? When I take and, take this and make a noise, like that, right? I made a noise, that noise went around the room, and then the noise went away, right? Is the energy gone? No, right? The energy just turned into other forms. I raised the book, that's the file, potential energy, right? And I started to slam it down, that's kinetic energy. I hit the table, I made some mechanical waves, some sound waves, right? I warmed up the table a little bit, yeah? And those sound waves traveled around the room, so warmth in the heat into the table, sound going around the room. That sound dissipates, it hits your ears, it activates your neurons in your ears, that's some of the sound energy dissipating. Hits the walls, heats up the walls a little bit, vibrates the walls a little bit, right? And that energy continues to change forms into more and more useless forms of energy, okay? I started off with a useful form of energy. I held this book up, okay? And then I turned it into motion energy, kinetic energy, to slam it down. And I continued to convert it into other forms of energy. Now that energy is still moving around the universe right now. That energy from that initial slam is still moving around, okay? And it will forever. The energy is conserved. It's just going to keep converting into other more and more useless forms of energy. This is the law of conservation of energy. Energy is conserved. Some things aren't conserved, though. Energy is conserved, but force is not conserved, okay? I can apply a force to this. I can also use things like leverage to apply more force to this and make it easier for me to lift it, right? I can use a compound or double pulley system. I can have the multiple pulleys wrapping around multiple times. Now it'll be much, much easier. I don't have to put as much force to lift that weight, okay? Force can be multiplied. Energy cannot be multiplied. Energy is conserved. There's a lot of conserved quantities in physics. Not all of them are conserved. For example, momentum is conserved in physics, but other things aren't. So we need to learn what's conserved and what's not. Here's your first thing that's conserved. Energy is conserved, okay? Energy cannot be created or destroyed. It can change forms. One form energy can take is matter. That means that matter can be converted into other forms of energy, which is the whole principle behind all the atomic weapons and all the nuclear power plants that we have. That's E equals mc squared. Again, that is the point of E equals mc squared, okay? The c squared, and I'll just tell you what the c is. The c is the speed of light, of course, but the c on that side of the equation, it's called a constant of proportionality. What it tells you is how much energy you get from some amount of mass. It's a conversion. It's a constant in the equation, okay? And you need to know nothing else but that. It's just a constant in the equation. To be specific, E equals mc squared is the rest energy or the intrinsic energy given by the mass of an object. You know that, like, you have energy sitting here because you're made of matter, right? But if you all of a sudden accelerate to, near the speed of light, you're going to have a lot more energy because you're moving fast, okay? And you know that because you know that you'd rather get into, if you're going to get into a car accident, you'd rather get into a very, very slow car accident than a very, very fast car accident, right? You and your car still have the same mass, but wouldn't you rather hit the wall at 1 mile an hour than 100 miles an hour? Yeah. Why would you rather hit a wall at 1 mile an hour compared to 100 miles an hour? Alexis, tell us why you would rather hit the wall at 1 mile an hour and not 100 miles an hour.
More force with the...
Yeah. Traveling at 100 miles an hour, you have more energy, right? You have kinetic energy because you're moving, okay? Traveling at 1 mile an hour, you've got much, much less kinetic energy. You're still made of the same mass, right? But you have much less kinetic energy, okay? Yeah, you're still made of the same stuff. E equals mc squared is the equation for rest energy, the energy of an object that is intrinsic to the object, okay? Energy equals mass. Energy can be converted to mass, mass can be converted to energy. So then you can ask the next level of question. You can say, well, what if I converted all of my mass to energy? What if I just poof turned into energy right now? How much energy would that be, okay? So let's give a number to it. A car battery operates at 12 volts of energy, okay? A volt is a unit of electrical energy. Remember the joule was our unit of like just energy in general? Well, the volt is a unit of electric energy. I won't tell you exactly what a volt is worth right now, like volts to joules. I won't give you that just at this very moment, but don't worry about it. We're using units of volts right now, unit of electrical energy. So a car's battery can output 12 volts of electric energy, okay? What is that enough to do? What can you do with 12 volts of energy? Think about what your car can do. Not ignore the engine part of your car. What's the battery running? Yeah, all the electronics in your car, right? Your lights, your stereo, right? Your heated seats and heater and air conditioning and all that stuff, right? All the electrical components of your car. 12 volts of energy can do that, okay? My diesel truck needs 24 volts of energy to turn the motor over, okay? Needs more energy for a bigger vehicle, right? Okay, get this. Take a single electron and take all of its mass and convert it completely to energy. It would give you 510,000 volts. A single electron, a single elementary particle, okay? If converted from mass completely to energy, 510,000 volts, okay? That's a lot bigger, a lot stronger than a car battery, right? Now a person, no, sorry, we'll get to a person. Now a proton. Take a proton, which is way bigger, about 2,000 times bigger than an electron, convert that into energy. Okay, if a proton converts completely into energy, it would be worth 938 million volts. Okay, almost a billion volts. Okay. Okay, now take a person. A person's made of a lot of atoms, right? That was just a single proton or a single electron. Okay, so take a person who's made of many, many, many thousands of trillions of atoms, right? They would be worth 10 to the 37th power in volts. So 4 times 10 to the 37th. This is scientific notation. Let me zoom in here. This is take the number 4, multiply it by 10, 37 zeros after it. Okay? And that's how many volts. It's a big number, right? It is a trillion, trillion, trillion. It's actually 10 trillion, trillion, trillion volts, right? It's just too big of a number to express in any other form but orders of magnitude or scientific notation, right? So yeah, you're worth a lot of energy, okay? But that's only if we converted all of your mass into energy, right? And that's not necessarily going to happen, right? You're going to stay as matter, right? You're going to continue to be matter because you're made of like stable matter. Your matter doesn't just like spontaneously convert into energy, right? But it could. Okay. So that gives you some relationship, so some perspective on, you know, how much energy really is there in mass, right? There's a lot of energy locked up in our mass, yeah? Mass can be converted into very, very large amounts of energy. Transducers are anything that converts energy from one form to another. You have something in your car and in your phones that plays sound, right? Speakers, yeah? That's converting electrical energy into mechanical energy. Your speakers are little vibrating, you know, discs, right? It vibrates and makes sound waves, yeah? Well, your car's speakers, your phone's speakers, they're converting electrical into mechanical energy. They're a transducer, okay? Your microphone, this microphone right in front of me, right? That's converting my sound energy, my words, right, into electrical energy so that it can be saved on my computer, okay? That's a transducer. In ultrasound, they use those probes, right, that they put on the skin, yeah? Those probes convert sound energy into electrical energy so we can see images on a screen, right? A light bulb is a transducer. It's converting electrical energy into electromagnetic energy, yeah? So converting electricity into light, right? A motor, right? If you have anybody have an electric car or a hybrid? No? All right. But you know that they exist, right? And you know that they're powered by electricity, right? And, you know, Tesla, right? You charge your little Tesla battery, and then you can zoom down the road, okay? That electrical energy is converted into mechanical energy, right? Battery turns into motion of a tire, okay, moving you down the road. That's done by an electric motor. That electric motor is a transducer, okay? Any device that takes energy and converts it from one form to another is a transducer. The X-ray tube is a transducer, okay? The X-ray tube, the X-ray machine takes electricity and converts it into X-rays, right? That's a transducer, okay? So transducer is just this very broad term meaning anything that takes energy and converts it from one form to another, okay? You're a transducer, right? You take the chemical energy you get from the food you eat and convert it mostly into heat, right? Some of it's into like your movements and your words and things like that and your thoughts, right? You're converting energy into different forms. Transducer is just this general term for anything that converts energy. So let me give you some options for different forms of energy, different forms energy can take. Chemical energy is the energy, well, locked up in chemicals, okay? You eat food every day, right? And from the food that you eat, there's three main things you're getting from food. Can you tell me what those three main things are? Protein. They're all nutrients, right? Proteins, fats, sugars. We call these your macronutrients. Yeah. So these are your main nutrients that you're getting, right? Which one of those three, proteins, fats, sugars, are the energy part of it? Sugars are carbs, right? So proteins give you structure, right? Proteins are what your body uses to build things with, okay? Similarly with fats, okay? But carbohydrates, the sugars that you eat, okay? Your body uses those to execute the cellular functions of your body. Your body uses the sugar for free energy, okay? That's taking the energy locked up in the sugar molecule and converting it, okay? Converting it from chemical into other forms. You know your body produces its own heat, right? Well, you're not getting that heat for free. That heat is coming from the conversion of chemicals into other forms of chemicals. Chemical energy changing forms, okay? Converting energy from the sugars you're eating into heat, thermal energy, okay? There's electrical energy. Electrical energy is just electricity, part of the electromagnetic phenomenon. Thermal energy is heat. Electromagnetic energy is what we think of as light, right? We know that we've learned things like X-rays can be harmful, right? X-rays can be harmful because they can deposit their energy into an atom that they hit, yeah? That's energy converting, energy changing forms. Nuclear energy, the energy locked up in the nucleus of atoms. You know that if you can take an atom and break it apart, you can get free energy from that. Okay, that's what power plants, nuclear power plants do. That's what the first atomic weapons did. They broke atoms apart, releasing huge amounts of energy from it, converting mass to energy. That's nuclear energy. And lastly, mechanical energy. It's the energy of motion. Mechanical energy can be divided into two subcategories. We have kinetic and potential. These are going to be very important, which is why they're on their own slide, okay? Kinetic energy, it's the energy of motion, right? When that pen cap was flying through the air, it had kinetic energy, right? If it hit one of you, I would have felt bad, right? Why would I have felt bad? Because the pen cap had kinetic energy, right? And it would have deposited that energy into you, and I would have felt bummed out because it hit you in the face or something, right? I didn't want to hit any of you. That's why I sent it that way, okay? Kinetic energy is the energy of motion, okay? That pen cap was sitting still on the table minding its own business. It's not going to hurt anybody, right? A bullet from a gun, it's not going to hurt anybody sitting on a countertop, right? But you convert the chemical energy in the powder in that bullet into kinetic energy, the bullet moving, it's going to hurt someone. What's up?
We're just going to go ahead and take a little break.
Okay, no worries. Okay. Potential energy is a form of mechanical energy. It's the energy of position, okay? So I usually like to pick things up and drop them when I talk about potential energy, okay? So take this folder. I usually have a book up here, but this is going to be a little nicer than the book. Take the folder, right? Leave it on the tabletop. Again, if I just leave the folder alone, it minds its own business. It's not going to do anything. I can leave the room, come back in a year from now, as long as no one touches that folder, puts any energy into it, it's going to be hanging out here, right? No potential energy, let's say, okay? But if I take this folder and I raise it up, I've put it into a different position, right? I've changed its position. What did I have to do to change its position? In terms of energy, what did I have to do? I had to put energy into it, right? I didn't get it up to, it's a couple feet above the table right now. It didn't go up there for free, right? I had to put it up there, which means I had to use muscles and stuff like that, the energy from my muscles, to lift the thing up, right? And I can feel it as I'm holding it up now. You can do this with anything that's in front of you, right? You can hold it up and go, yep, it takes some energy to hold that up, right? I can't hold it up for forever because I'm going to run out of energy, right? But I did. I put energy into it to bring it to this position. Now that I've put energy into it, does it have more energy than it did sitting on the tabletop? Yeah. What kind of extra energy does it have now? Potential energy, right? Because it's in a position, okay? And it's in a different position. It's in a higher potential energy position than it was sitting on the tabletop, okay? I can bring it a foot above the table and give it some potential energy, or I can bring it 2 feet above the table and give it more potential energy, okay? What's going to happen when I let this thing go?
Kinetic.
Yeah, it's going to fall, right? Which is going to take the potential energy and convert it into kinetic energy, okay? So we do it, we let it fall. As it's falling, I let it go. As it's falling, what kind of energy are we losing as it's falling? Potential. What kind of energy are we gaining? Are we gaining the kinetic energy for free? No, we're just converting, right? We're converting from potential to kinetic, okay? At the time when it hits the tabletop, so we hit the table, I have the least potential energy, but at that split second when I hit the tabletop, I have the least potential, but I have the most kinetic, right? And say I have 0 potential energy here and maximum potential energy here, right? As I let it fall, I convert potential to kinetic. So when I hit the table, I have my least potential energy, but I have the most kinetic. I've converted all the potential to kinetic energy, okay? And then it hits the tabletop, right? And it converts into other forms of energy. You heard it, right? So it's some mechanical energy. If I did this a bunch of times, I could touch the tabletop and feel that the table is warm, a little warmer there, right? I'm putting energy into the table. I've took all that kinetic that I got from the potential, and I put it into the table and the sound that I've made in the room, okay? So now, instead of raising it 2 feet, I raise it about 1 foot above the table. What kind of energy do I have less of at the 1 foot position? Potential, right? I have less potential here than I did up here, right? So when I let this go, I'm not going to have as much potential to convert to kinetic as I did when I was up higher, right? So what did you notice when it hit the table? How was the sound different?
It was less.
Yeah, so like, let's go again, it's a couple feet up, right? Now 1 foot up. A little quieter, right? Just a little bit quieter, okay? Why was it quieter?
It had less potential.
Yeah, because I put less into it, right? I gave it less potential at this lower position, so it had less to convert. Energy doesn't come from nowhere, right? It came from somewhere, and so I just have less to convert if I put it into a lower potential position, okay? This is why, it's more dangerous to climb up on the, a 10-foot ladder than it is to stand here on the floor, right? Because up on the top of that ladder, I've got a lot of potential energy. I've put myself into a position where I can convert a lot of energy, right? But here on the floor, I've got less of a potential. Okay, I've got much less potential energy. So the safest thing to do, lay down on the floor. Don't move. Never put yourself into a potential position to get hurt. Okay, that's the idea though, right? That's mechanical energy. Mechanical energy we divide into kinetic and potential. Kinetic is the energy of motion. Potential is the energy of position. And we can convert them, okay? I can take this, I like pens and pen caps, right? I can take this pen and I can just give it kinetic energy, right? I can throw it upward, okay? It gets to a position, right, where it has the highest potential. And then what does it do? It falls back down, right? It's gonna fall faster with more kinetic energy the higher I throw it, right? So if I throw it like this, less kinetic energy as it falls back down. If I throw it higher, we measured its velocity coming back down, it would just have more kinetic energy on its way back down because I put more potential into it, getting it to that higher point in the room, okay? So that's the story. We can convert these forms of energy from one to the other. I can convert kinetic into potential, such as when I threw the pen up, kinetic energy going to a high potential position. And then as it falls, it goes from potential to kinetic, right? We're just converting energy into different forms. Was energy lost along the way? Well, the law of conservation says no, but you're saying yes, and I think I know why you're saying yes, but tell me why you're saying yes.
it's coming back to its original point.
Yeah, its original position, right? I throw it up, comes back down to its original position, right? I put energy into it, put it up to a high, I gave it kinetic to go up high, to fly up high, and then it reaches its maximum potential, then it falls back down, gaining kinetic on its way down. So we went from kinetic to potential, potential to kinetic, right? Then it hits my hand, okay? And stops. It loses all of its kinetic when it hits my hand, right? So 0 kinetic, 0 potential when it hits my hand, made some noise. I didn't lose any energy on the way, right? I think I thought what I thought you were getting at is some of the energy of it going up was lost to just air friction, right? But we're almost going to just consider that negligible for our talk. But if you wanted to be nitpicky, you could say, well, yeah, I put some energy into the air. The air in the room kind of wiggled around when I threw the pen through it, right? But the idea is that the energy was conserved, right? It only had, on its way down, it cannot gain more kinetic energy than I gave it in potential, right? It just can't. Okay. Potential and kinetic are going to become important inside of atoms. Okay, I'm not giving you this whole talk so we can understand how pens can move and fly around rooms, right? I'm doing this whole talk so we can understand how energy is conserved and exactly what forms energy takes so that we can talk about atoms, okay, which is the subject of next class. So let me give you the law of conservation of energy within an atom, okay? The pull of an atom's nucleus, Marco, what's the charge of the nucleus of an atom? Positive electric charge, right? Okay. And orbiting around the nucleus are electrons, which have a what kind of charge? Negative electric charge. What do we know about opposite charges? They attract each other. Yes, excellent. The pull of an atom's nucleus on the orbiting electrons is electromagnetic, right? It's a positive and negative electric charges pulling on each other, right? But it is kind of like the pull of gravity on any object, okay? Gravity is attractive always, right? And in this case, inside of an atom, positive, negative charges, they're attractive. So it's kind of like the pull of gravity, okay? Don't let the analogy go too far, but it's kind of like the pull of gravity. So if an electron is in a low position, a low orbit, an orbit near the nucleus, it's in a position of low potential energy. Okay. If an electron is at a higher outer orbit, it's in a position of higher potential energy. Okay. The potential energy of an orbiting electron can be represented by the height of its orbit above the nucleus. That means when an electron goes from a high orbit to a lower orbit, it's going to lose potential energy. Okay? But what did we say about the law of conservation of energy? Energy's not lost, right? So if I go from a high potential energy position in an atom to a low potential energy position, I've lost potential energy. But I didn't lose it, right? The energy will have to convert into another form, okay? The lost potential energy from electrons moving downward from high orbits to low orbits must be accounted for, okay? So here's the trick. When in an atom, an electron drops from a high shell position, an outer shell position, to a lower shell position, its potential energy that it had purportedly lost, right, is not lost. It is converted into a different form of energy called electromagnetic energy, or a photon of light, okay? This is where light comes from, period. Light comes from electrons moving from high potential energy positions to low potential energy positions. All the light that you're seeing right now is because in an atom inside of that fluorescent bulb, some of the gas inside of that bulb was energized. The electrons jumped up shell levels and then jumped back down. When they jumped back down, they had to lose potential energy. And we just learned that energy is not lost. So it converts into electromagnetic and light comes out of that light bulb. Okay? We can also call it electromagnetic potential energy, but you can just call it electromagnetic energy or light, right? It's all the same thing. This comes out in the form of a light wave, if it's like a light bulb in your room, or X-rays, if it's the X-ray machine. We give names to the shells that the electrons sit in. The innermost shell is the first shell. We refer to the first shell as the K shell. There's no good reason for that. K does not stand for anything. Okay. You guys know like EKGs. Who's done an EKG? All right. So you guys know like there's the PQ, RS, and T waves. Does PQ, RS, and T mean anything? No. Like you know which one's the P wave, right? But we could have easily called it wave 1, right? The P, Q, R, S, and T mean nothing, right? There's no names attached to them. Same thing in atoms. K, L, M, N, O, and P are the names for the shells, but they don't stand for anything. They're just placeholders, right? It's because A, B, C, D, E got taken by, the earliest people to name things in science and math. So we use K, L, M, N, O, and P, okay, for atoms. K shell's the inner shell. After K in the alphabet comes L, so the L shell is the second shell. Then M, then N, then O, okay? The L shell is further away from the nucleus than the K shell, okay? So the L shell has more, the electrons in the L shell have more potential energy, right? Standing on the floor here, I'm in the K shell. Standing on the chair, I'm in the L shell, right? I have more potential energy when I'm standing on the chair, right? I feel a lot higher up in the room right now, and if I fell, I'd hurt myself more than if I fell from the ground level, right? Okay. When I go from the chair to the ground, I convert, right? I convert potential to kinetic. You notice I fell towards the ground, right? When I hit the ground, I made a little sound, I wiggled a little bit, right? All of that was conversion of energy. Well, if I was the electron, when I jumped from the chair to the floor, I'd emit a photon of light. I emit a light wave, okay? Shown here. So an L shell electron falling down to a K shell emits a light wave, okay? I haven't told you exactly how much energy that light wave is going to have because you don't know how much potential energy this has here and what the potential energy here is yet. We're going to do that in the next lecture, okay? But that's the deal, right? And here's what's cool. It works the exact opposite direction, okay? If an electron can fall down and emit a photon, then an electron in a low position can absorb a photon and go up, okay? That's shown here. The absorption of an X-ray or light photon can lift an electron to a higher orbit. That's converting electromagnetic into potential, right? That'd be like I'm standing here on the floor and something zaps me and I jump up and on top of the chair, right? Something put energy into me and I jumped up on the chair, okay? And then if I want to convert that energy back, I can hop back down to the floor again and just re-emit that energy, okay? It works both ways. Electrons can emit photons of light by losing potential. They can also absorb photons of light by gaining potential. This is huge. This is a huge understanding. This was figured out by, no one else but Einstein in 1905. This is what Einstein won his Nobel Prize for, was this whole idea about the emission of absorption, emission, electrons, and photons of light. He called it the photoelectric effect. Okay. That all brings us to the idea of quantum physics. So we're not going to talk, this is literally the only slide on quantum physics in the whole thing. Okay, you probably heard of quantum physics. I've studied it. This doesn't really give you any kind of really true insight into it, but let me give you an idea. The name quantum physics came from the early days where they were proposing whether or not light came in individual pieces or it came as a big bulk wave, okay? When we learned that light was emitted from atoms in individual photons, which is the photoelectric effect that Einstein figured out, what I just kind of showed you, we called the light quanta. Quanta as in a number, a piece of light, right? One quantum of light, okay? That birthed the whole field of quantum physics, how atoms and light work, okay? We now refer to light as photons. photons or quanta. They've also been called corpuscles and other names like that, but they're quanta or photons. I will most of the time just call them photons. The study of all the relationships and interactions between atoms and the waves of radiation they either emit or absorb, that's called quantum physics, okay? Hugely interesting, huge implications for what the world is and does, but we don't get to talk about it in this course because it's a lot of information. I encourage you, if it sounds at all interesting, to look into it. I've got just so much material that I can point you towards, but that's all we get for quantum physics. Let's move on. So now we're going to talk about, rather than talking about the, an individual atom, which we will do next time, let's talk about how matter behaves when you get large collections of atoms, okay? When you have more than one atom, you can start to talk about things like heat and the states of matter. So let's start off with the states of matter. There are 3 familiar states of matter that you know. You know about solids, liquids, and gases, right? Anything that's matter can be a solid, a liquid, or a gas, okay? Anything. Even, metals, right? Metals can be solids, liquids, or gases. You can take a chunk of iron, which is a solid usually, right? And you can heat it up. Put heat into it. Put heat energy into it. And you can turn iron into a liquid. If you heated iron up hot enough, you could turn it into a gas, okay? It's just that here on Earth, we usually find iron as a solid because we're not very hot, right? That's good for us because we want to sort of stay as a mostly solid/liquid thing, right? You're mostly liquid, by the way, right? 75 to 80% of you is just liquid, okay? Some of you is gas, right? Different things, but think about the oxygen in the blood and things like that. That's as a gas. And some of you is solid, right? Your connective tissue, your fat, your skin, your organs, all of that. Those are mostly solids. So we have solids, liquids, and gases in our own bodies, okay? Also, parenthetically, these are not the only 3 states that matter can be in, okay? These are the 3 most familiar states, okay? There are states above gases, such as plasmas, and then there are states below solids that are called condensates. There's different names, but anyways, these are the 3 familiar ones, okay? So don't take these as being the only ones. How are they different? Because anything can be a solid, a liquid, or a gas if you change its temperature, right? So here's how solids are different. Solids have a definite shape, definite volume, okay? A solid thing doesn't change its shape easily, okay? And occupies a set amount of space. That's volume, okay? So I can't pour a solid into a container and have it take the shape of a container because solids don't pour, right? Okay. Liquids have indefinite shape but definite volume. We can take the water from Enrique's bottle and we can pour it into Lewis's bottle, okay? It's going to take up just as much space in Lewis's bottle as it does in Enrique's bottle, right? But it's going to be a different shape because these 2 bottles are different shapes, right? Take up the same space but be different shapes. Indefinite shape, definite volume, okay? Whereas gases have indefinite shape and indefinite volume, okay? We take a tank of oxygen here on the counter and we open it up, okay? That oxygen is going to fill the shape of this room, right? If I take that tank of oxygen and put it into a completely differently shaped room of a completely different volume and open the tank up, guess what? It's also going to fill that room, okay? No matter what the shape is and no matter what the volume is, gases tend to spread out, okay? I can release that tank in a room this big, or I can release that tank in a room the size of our break room, and either way it's going to fill the room, okay? No matter the shape, no matter the volume, gases are indefinite in shape and indefinite in volume. So that's what we think about as the states of matter. Now, matter can change states, okay? And we have names for these things, right? So when solids change to liquids, what do you have to do to a solid to change it to a liquid? Heat it up, right? That's a change in its state. What does it take to change the state of an object, of matter? Took energy, right? You had to do work to it. Yeah, you had to put energy into it. We call that melting, right? Solids to liquids, we say that's melting. Everyone knows that, I think. And you probably also know that when a liquid turns into a solid, we call that freezing, right? So these are not foreign names to you, right? We say things condense when they turn from gases to liquids. You know about condensation, right? Like on a day when it's cold outside or something like that, right? You get condensation on your window, right? You get a little bit of wet on the windows of your homes and stuff. Gas to liquid. Evaporation, liquid to gas. Okay. What's an example of? Are you familiar with any substance that has all three forms? That undertakes all three forms? Oh, so plasma is the next step up from you said plasma, right? So plasma is the next step up from this. We won't talk about plasma here, but can you think of something that you use in your everyday life that you see in all three forms? Solid, liquid, gas. There's at least one thing. You need it to survive. Water, right? What's the solid form of water? Ice. Do you have ice at home? Yeah? Okay, good. What's the liquid form of water? Water. What's the gaseous form of water? Vapor or steam, right? You have ice cubes at home. You drink water, right? And when you boil water, you make steam, right? You are familiar with all three of these states, and you're familiar with changing these states from one to another, right? You get ice cubes in your cup and you know they melt, right? You put a ice tray in the freezer, you know it goes from liquid to solid, right? And then you take a pot of water and you boil it, convert it into steam, right? Okay, so you're familiar with these changes. Now, here's what's cool. These changes have a threshold, okay? For example, do you guys know what temperature water boils at? It's 100 Celsius. Thank you for giving me it in the metric system. Unfortunately, we use the Fahrenheit system here, typically, right? So it's 212 degrees Fahrenheit. I don't like it. I like 100 Celsius, right? Because I know 100 Celsius is when water boils. That's what, by the way, that's what the metric system for temperature, the Celsius system, that's what it was made for, right? 0, water freezes, 100, water boils. It was built off of water, okay? Fahrenheit system is not built for that. It was built for a different reason. But anyways, water boils 212 degrees Fahrenheit. In Fahrenheit, when does water freeze? 32, very close. And in Celsius, it freezes at 0, right? These are points. These are freezing points. These are boiling points, right? Water does not boil at 211 degrees Fahrenheit or 99 degrees Celsius, right? Those aren't the same, but you get the idea, right? Water doesn't boil at 211. It boils at 212, right?
What's that thing? There's that thing when people grab bottles and you just smack it on the table and just freeze
Yeah, because it's right at that phase transition. So yeah, what he's talking about is take a thing of water, right, and get it to almost freezing. Okay, and so you put it in the freezer. You've sucked a bunch of energy out of the water, and it's almost frozen, right? And if you change the state of that water very quickly by usually like they smack it on the countertop or something, it takes it that one, it's like straw that broke the camel's back, right? It's almost ready to freeze, yeah, and you just put a little extra energy into it and it converts, it changes phase, right? You can also do like you could take boiling, I'm trying to remember this exactly. You can take boiling water, which is almost ready to convert to steam, and if you're in a very cold environment, like it's snowing outside, you can take that boiling water and chuck it, and it will convert from liquid to steam instantly, right? It changes phase very quickly because you're taking it to almost that phase transition, right? So that's what we call it. We call these phase transitions, okay? Let me rephrase that. Almost all forms of matter have very specific phase transitions, points at which they go from solid to liquid and liquid to gas. It's not a slow, continuous process. It doesn't happen, then does happen, okay? Now, water, we know water, right? We know water's easy. I just told you the numbers for the exact phase transition numbers for water, but everything's different. Everything has different solidifying points, so melting points. Everything has different boiling points, but water is an easy and knowable one. Okay, good. Also, earlier when I was talking about the air, I said you can kind of think of the air as a fluid, right? Fluids do not mean liquids. Fluid and liquid are not an interchangeable term in physics, okay? I know like most of the time we think fluid and liquid are sort of interchangeable. Fluid is anything that flows. Liquids and gases flow, okay? So gases are fluids. So if you took a fluid mechanics course in a college level fluid mechanics course, right? You're going to learn about liquids and you're going to learn about gases, okay? They're both fluids. The next one is sort of a funny one, resins. Resins are types of matter that do not have a phase transition or a threshold for changing state. They don't have a melting point. Think about like rubber, right? You ever melted rubber before? It doesn't all melt at once. It sort of takes more time to melt, right? It changes phase very slowly, and with most of these resins, you can heat them, shape them, and let them cool down, and they can retain their new shape, right? That's how they take and they mold all the plastic parts that everything's made out of nowadays, right? They take the plastic resin, they heat it up, they inject it into a mold, takes the shape of the mold, because liquids take the shape of whatever you put them in, right? And then it cools down to a solid, like my computer, right? All these parts for my computer, this thing, right? It's all plastic. They took and heated up that plastic resin, injected it into a mold as a liquid, and then let it cool, and it became a solid again, right? Now it's a solid, right? So all this, the cases for your, the cases for your phones, the plastic thing that my microphone's made of, this thing, the bottles, right? All of those are made of plastics, and plastics are resins. Resins don't have the same properties that other materials do. Resins are kind of special, right? We haven't had plastic for forever. We had to make plastic, yeah? Okay. The next thing I want to give you, and it was one of those things for me that really, really struck me when I was a student learning this stuff, is the idea of cold and hot. Okay, and I remember all the way back to third grade when I was getting like sort of, in third grade you're kind of getting your first sciencey type stuff, your science talks from your teachers. So I remember all the way back to third grade when they were talking about heat, and I remember learning that, there is, and I remember the teacher said it very specifically, there is no such thing as cold, okay? And I was thinking, why should there's no such thing as cold? Like, I felt cold stuff all the time, right? There is no such thing as cold. There's just more or less heat, okay? Cold is a name we give to heat, things that are hot, but not as hot as we are, right? Anything that's less hot than you feel it and you go, that's cold, right? Cold's just a name we gave to things that have less heat than we do, okay? So cold is really just absence of heat, okay? In order to understand what that means, in third grade I didn't really get it, right? It took a while, took till my adulthood to really understand what that means, partly because I didn't listen to science in high school, right? Took till I got all the way to learning about radiography to understand this, right? Heat is not a thing, okay? We talk about like heat flowing from one thing into another, right? And you can almost picture heat being like a thing that comes from me to you, right? Or from one substance to another, yeah? But it's not. Heat is not a thing, okay? So let's learn what the heck heat is then, okay? So for one, when an object is said to cool down or lose heat, the heat didn't flow out of the thing and go somewhere else. And if an object heats up, the heat didn't flow into it, okay? Energy doesn't disappear. When a substance cools, its heat energy, and I know they say flow, right? Its heat energy is transferred into the surrounding substances, the surrounding material, okay? This is why the vacuum sealed, you've got a vacuum sealed, Fabian, you've got a vacuum sealed bottle there, your yellow bottle, right? It's one of those vacuum deals, right? And it probably keeps water cooler for a lot longer than Lewis's or Enrique's bottles, right? Okay. Because there's two walls to that bottle, right? There's the outer wall that we could see, and then there's an inner wall, right? And inside the inner wall, you put the water. Well, between the outer wall and the inner wall, they've sucked out all the air. There's a vacuum chamber between the inner wall and outer wall, okay? The heat from out here can't get to the inside water because heat moves through matter, okay? Heat's gonna move through the matter. Heat is really just the motion of particles. Heat is the internal motion of particles in matter, right? Everything's always jiggling and vibrating, the matter that everything's made of. And when things are jiggling and vibrating more, we call them hot. When they're vibrating and jiggling less, we call them cool, okay? Heat, the flow of internal energy from one molecule or object to another. I hate the word flow, and I'll put that on record. It's recording me saying that. I hate the word flow because nothing's flowing, okay? We're just transferring energy from one object to another, okay? So there is no thing called heat flowing back and forth between me and you, or from hot thing to a cold thing, right? Heat is energy. It's thermal energy, okay? And we know that energy changes forms, right? So there's two things here: internal energy. There's kinetic energy. Kinetic energy is the temperature. So you have you take a pot, boil the water, right? When the water's right at that boiling point, just before it turns into steam, those H2O molecules are all bouncing around very fast with each other, right? What happens to you if you dip your finger into that container of water that's boiling? You get burnt, right? You get burnt, so you think heat flowed into my finger, right? Well, what actually is happening is the molecules of water are jiggling around really, really fast, right? And they're bumping into your molecules faster and with more energy than they do when they're cooler, okay? A cool thing of water, right? Take a water, it's about to freeze, take it out of the freezer, put your finger in it, it feels cold, right? Because you're conducting your heat energy into that water. Your molecules are moving more than the water's molecules are when it's colder than you, okay? And this goes back and forth. We talk about heat flowing, but nothing's flowing. There's no thing called heat flowing. It's just the thermal energy due to the motion of molecules. We say the temperature of a room, like it's 70 degrees in the room right now. That temperature is a reflection of the average kinetic energy of the air molecules in this room. When it gets hotter in this room, the average energy of the air molecules goes up, okay? They're bumping into you with more energy now, okay? Gets colder in this room, the average energy of the molecules is going down. Kinetic energy, to be specific. When a substance is heated, the flow of energy into it may cause it to either increase its temperature or change phase. Go from a liquid to a solid, for example, right? Change a liquid to a gas, right? Changing phase is what happens. We can put energy into an object so much that we change its phase, a phase transition. Solid to liquid, liquid to gas, and so on. So, then we want to ask, what ways do we have of changing the energy of matter? How do we put energy, when they say energy flows into something, what's doing the flowing? How do we flow energy from one thing to the next, right? So there's three ways of heating something up. You have conduction, convection, and radiation. Now, conduction is direct contact, okay? If you're sitting in your chair like you have been for the last, what have we been sitting down for? Well, at least about almost an hour now, right? Yeah, my lecture notes started an hour ago from this talk just now. So we've been sitting for an hour since I gave you guys your break. If you get up out of your chair and feel your chair, what do you expect to feel? Warm, as compared to the chair next to you with no one sitting in it, right? Good. You conducted heat into that chair, okay? Because you're warmer than the chair, yeah? The chair is going to be room temperature, so 70 degrees, right? What's your body's surface temperature? 98.6 on average, right? So you're on average 28.6 degrees warmer than the room around you, at least if the room's 70 degrees, like we assume this room is. You're going to conduct heat into the chair, okay? You're going to warm the chair up. Now, the chair's never going to get hotter than you, right? You can't make the chair be warmer than you are. You can only conduct enough heat into that chair to heat the chair up to your body temperature, right? We'll talk about conductors more later. Convection deals with fluids. Remember, fluids are liquids or gases, right? So a warm air mixes with cold air, right? We get all these weird atmospheric phenomena where warm air and cold air mix, and you get hurricanes and tornadoes and all that funny stuff, right? Well, those didn't come out of nowhere, right? Those came from energy deposited into these big atmospheric systems, right? Hot air and cold air mixed together, that's convection, okay? You guys probably have a convection of it at home, okay? Even if you have a little countertop one, it's your air fryer, okay? You got air fryer? You guys an air fryer? Yeah. That's what it is. It's a convection oven, okay? Some people's ovens are convection ovens nowadays because air fryers got popular a few years ago. That is the mixing of hot and cold fluids, okay? The hot fluid will warm up the cold fluid. That's convection. And radiation. Radiation's our last means of transmission of heat. Electromagnetic waves conveying conveying energy from one object to another. Now, radiation's the one that doesn't require direct contact, right? Radiation is part of the reason why Fabian's water in his bottle is gonna get warm eventually, okay? His bottle's really good about not conducting heat from the outside world into his water, right? But it's not so good at shielding from, radiation, okay? So it's gonna warm up eventually, right? The infrared radiation in this room coming off of you is gonna eventually warm that bottle up, okay? Warm the water in that bottle up, right? Regardless of how good the vacuum chamber is to separate water from the outside world, right? Radiation does not need a medium. It doesn't need to travel through anything. Radiation can travel through empty space, right? We learned that because we learned that we get the light from the stars that are out in outer space, right? And there's nothing between us and them. Okay, so let's talk a little bit more about conduction, okay? What I want to focus on here with conduction is objects. Yeah, go ahead.
Thought about when like you're, what is it called? Like you're on the carpet.
Yeah.
Is that convection?
You talking about the static electricity?
You like shock someone?
So no, that's electromagnetic. It'll be electric discharge, electric energy. But let me give you a carpet example, right? You can just do it with chair or tabletop, right? The tabletop here is the same temperature as your chair, okay? But you can do this with the metal of the chair and the fabric of the chair, or the tabletop and the fabric of the chair. But touch the fabric of a chair, any of these chairs in the room. Don't use these vinyl ones. Like touch one of these, right? Feel it, or even touch your clothes and feel your clothes, right? Feel the warmth of that, and compare that to either the metal of the table or the wood of the table. Do they feel different? Which one feels colder? Table, right? Are they colder? Is the table colder than the chair? No. You know how we know they're not colder? Because they're in the same room and they have been in the same room since forever, okay? These have equilibrated to the temperature of this room. The chair fabric is the same temperature as the table, okay? Does anybody have like wood floor or tile at home? Tile is a good example. You have tile? When you step onto the tile barefoot, how does it feel? Cold, right? How about your carpet? Warm, or at least not cold, right? If it's a very cold winter morning, what would you rather be walking on, carpet or tile? Carpet, right? Well, guess what? The carpet and your tile have both been in your home for the same amount of time, right? They are both the same temperature, okay? Your tile is the same temperature as your carpet. So why do they feel different? Tile, wood, metal are all better conductors of energy, of heat energy, than the fabric of your carpet or the chair is, okay? They're the same temperature. The tile is a conductor, the carpet is an insulator, okay? Conductors transmit heat quickly. That's why when you step onto the tile, you feel cold because it's sucking all that heat out of the sole, the bottom of your feet, right? But when you step on your carpet, they transmit heat poorly. You don't put much heat into that carpet, okay? So you get to keep it, which makes you feel warm. Conductors transmit heat readily, quickly. Insulators transmit heat poorly. Excuse me. So, instead of being barefoot on your tile, you go put on your house slippers or something, right? Or your socks, for example, right? Now you have an insulating barrier between the tile and your feet. Right? It's like you're walking on carpet the whole time now, right? Your socks are a great insulator. And they actually give that example. When stepping from carpet onto tile, your feet feel cold, not because the tile is colder than the carpet, but because the tile is a better conductor of heat. And also, too, like, you know, if your home was very hot, right? If your home was heated up to some crazy temperature, okay? You would rather step on the carpet than the tile, because the tile would burn your feet, right? If the tile gets hot enough, it'll burn your feet, yeah? Whereas the carpet wouldn't. You know, you go outside on a hot day, right? You probably don't want to be stepping barefoot on the concrete or blacktop, right? Anybody live in the valley where we get like 120 or higher, right? You don't want to step on the blacktop with bare feet because you're going to get your feet burned, right? But you can stand on the grass. The grass and the blacktop are the same temperature. Okay? The grass might still be hot, yeah. But they're the same temperature, but one of them's a better conductor of heat than the other, and you're going to get burnt with the one that's a good conductor of heat compared to the grass. Okay? So there you go. Now you know that heat's not a thing. It's not a substance. Heat is the internal motion of the molecules that something's made of. Okay? Something is hot when its internal molecules are moving faster than you. Okay? Something is cold when its internal molecules are moving slower than yours are, okay? And all objects will either be conductors or insulators. There's better or worse conductors and insulators, okay? Certain things conduct better than others, but we can categorize into those two categories, conductors and insulators. And I'm giving you a couple examples of you know, where you can find each in your everyday lives. All right. The last thing is radiate. Just a quick little last talk about radiation, and I think this was another whoa kind of a, you know, big light bulb moment for me. Now, let me be clear: the sun is hot, okay, but when you're here on Earth, not next to the sun, you're not feeling the heat from the sun, okay? When you feel warm, standing out in the sun, it's not that the sun is carrying some, remember we just said heat's not a thing, right? So it's not that there's some heat that came from the sun and is now getting to you, okay? The sun emits waves of electromagnetic energy. Those waves of electromagnetic energy have no intrinsic temperature of their own. Remember, heat's not a thing, okay? Those electromagnetic waves come from the sun and they hit your body, okay? And those electromagnetic waves carry energy. And what can energy do? Remember, what was energy? The ability to do work, which is to change the position of matter, right? Specifically, your electrons in your atoms, okay? When the rays from the sun hit your skin, they make your atoms jiggle, okay? They make your atoms vibrate more than they were before that, okay? You are getting hotter. The sun is not transferring heat from it to you, okay? The sun's rays are depositing energy into you, and you are heating up, okay? So you do get warmer. You do get warmer in the sun, but it's not that the sun is carrying heat from it to you, okay? The sun's rays carry energy. That energy warms you up. Molecules in your skin absorb the energy. They vibrate and shake, manifesting more kinetic energy as temperature, okay? So, to be clear, it's your skin that's hot, not the radiation. Kind of cool, right? Sun's not carrying any heat towards you. It's got no intrinsic heat of its own going from it to us. We just jiggle more. Yeah, we vibrate more. All right, so let me finish this up by giving you the how this applies. All three of these things apply with just inside of an X-ray tube, okay? So here's a picture, cartoon example of an X-ray tube. In an X-ray tube, all three methods of heat transfer get used. For one, bombardment of the X-ray tube's anode with billions of electrons, that is cathode where my laser pointer is, shoots electrons toward this disk called the anode. We heat up the anode, okay? That energy is dissipated in forms of radiation. Those are the X-rays we emit. Here's what's interesting. More than 99% of the energy that we make during an exposure, when we energize the X-ray tube, more than 99% of that energy is converted into heat, thermal energy. Less than 1% of all the energy we use to produce X-rays actually produces X-rays. Most of it's waste energy. And that too, like, you know, when you charge your phones, right? You know your phones get warm, right? That's wasted heat energy, okay? Electric electric devices are intrinsically inefficient. They make a lot of wasted heat. Okay, there's a lot of work in condensed matter physics to produce materials that waste less heat. The less heat you can waste, the less energy you have to use, right? Okay, anyways, so radiation comes out of the anode. Heat, the anode heats up. Heat is conducted down the shaft, if you kind of follow the laser pointer that I'm using, down the shaft of the anode. Heat is conducted into the shaft of the anode. And then cooling currents, cooling convection currents, are circulated in the oil bath around the anode to cool the thing down. So we have convection in the fluid, we have conduction in the anode heating up, and we have radiation being emitted in the forms of heat, visible light, and X-rays coming out of the anode disc inside of the X-ray tube. So this disc here is where the X-rays are coming from inside of the X-ray tube, but all three means of heat transmission are being used here: radiation, conduction, and convection inside of the X-ray tube. And that, thankfully, is the end of our talk today. That was a lot of work we just did. We made through a ton of material today. I encourage you to go and review this stuff. I'll get my videos uploaded as soon as I can.